All right, guys, welcome to grade 12 physics. And our topic for this moment, for this series of lessons, will be momentum and impulse. So with physics, it's always building on things we learned from grade 10 and 11. And there's a lot of definitions that we are going to need to remember. We're going to learn fresh ones. We are going to link concepts together. And we are going to calculate and apply. So for today, I want us to build. Let's build foundation, please. It's going to be a very, very detailed note. With this note, you don't need any other thing. So please keep the notes and just add on to it when you get back to class. But I doubt if there's anything you would be adding on. You'd rather be underlining and re-emphasizing. So let's look at momentum. Okay, so we're going to look at momentum. The first thing that I'm going to ask us to do is to quickly define momentum. All right. We'll start by, let's say, symbol. Symbol is a small letter P. Definition. And from that definition, we're going to start going wild now. It is the product of mass and velocity of an object. 2 marks in the bag. Momentum is the product of mass and velocity, which means we can move to our formula. Small p equals to m times v. And once we get to formula, the next thing will be units. The unit of momentum. So you know that this is what? Kilogram. And speed is, or velocity rather, meters per second. All right. Now we are going to say plus direction. Why am I bringing in direction? So we're saying kilogram, meter per second, and direction. Why are we bringing in direction? Let's talk about the quantity. Momentum is a vector quantity. That is, has both magnitude and direction. It has both magnitude and direction. So every time we do this, please, direction is important. And I think it is important for me to say an object at rest has 0 momentum. I hope that makes sense. Since velocity equals to 0, mv will also be equal to 0. That's very, very important. When an object is at rest, its momentum will be equal to 0 because its velocity so equals to 0. Guys, I want us to build. Make sure every slide makes sense to you. Every slide must make sense. Example, calculate the momentum of let's say of an object of mass 2 kg moving at 6 meters per second west. Just a basic example that I know you can quickly figure out. Calculate the momentum of an object of mass we need to know that the mass is always in kilogram. I'm going to emphasize that. And our velocity is in meters per second. Okay, now, I think this is very straightforward. mv, 2 multiplied by what? 6. 12. Mass is what? Kilogram. Velocity is meters per second west. I hope that makes sense. And just a footnote here for conversions, in case we have forgotten. To convert grams to kilograms, because mass must be measured, what do? We divide by what? 1,000. So please take note of that information. Divide by. That is our first one. Yes, talk to me. So you've got to move. You've got to move. You've got to move. This is matric. You are no longer in grade 10, remember? So you've got to come with a pace now. The year ends by June. Okay, so catch up quickly. Maybe you just logged in now. We've got to catch up as quickly as possible. This is grade 12. Things are on a fast pace. Momentum is the product of mass and velocity. Now, to convert, I said to get grams. I'm supposed to convert. Now, these are revision. A lot of things here are revision. To convert kilometer per hour to meters per second, what do? Now, a lot of people always try to cram the 0.28, which I don't really like, or 0.36. So you see, I don't really like that. So what I do is, I multiply it by 1,000 and divide by 3,600. Always easy, because my kilometers, the K is 1,000. And the time there is 3,600 seconds, make 1 hour. So those are basic things that we ought to have at the back of our mind right from grade 10. The only new thing is just the definition. And from the definition, you have the formula, you can just apply. Hi, Noku.
Hello, sir.
I thought you were now in Kuvukiland somewhere.
No, sir, I'm here.
Okay, good to see you again. I had Noku, we came a long way. Let me see who else is a familiar face from Tekufat. Yes, Tekufat also here. I'm glad. Who else is here? Wait, there's somebody that says even me. Felicia, you only rocked in December, I think. These ones we've weathered the storm together. Let me see. But most of you have stayed on from the grade 11 class. That's good. All right, are we all on the same page now? Oh, okay. McLaren, all right. McLaren. Okay, all right, no problem. No problem. Okay, guys, are we okay with our first slide? Are we okay? Are we okay? All right. All right, so you must learn to catch on quickly now, all right? Catch on very fast. You've got to learn to increase the pace. So momentum is a product of mass and velocity. Please don't let's forget our definitions. Don't forget your definitions. Who is busy with doing so many things there? Boy Pillow, is that you? Okay. Guys, can you still see my screen? Just to make sure. Okay, all right, good. So, please, very important, the definition. Product of mass and velocity. That formula is given on the formula page. P equals to M times V, where M is the mass measured in kilogram and V is your velocity measured in meters per second. Momentum is a vector quantity because it has both magnitude and direction. And if an object is at rest, velocity is 0, it means momentum would be 0. That's just a basic entry-level example, and this is just to remind you of basic things that we need to learn. All right, since momentum, we're going back to grade 11 now, or grade 10. Since momentum can be represented, since momentum is a vector quantity, it can be represented as a vector arrow. What do I mean by a vector arrow? We have that, where the length of the tail, so that's going to be my tail, shows the magnitude, that is the size. And the arrowhead would give me what? The head here would give me the direction. So it can be represented, I'm sure you remember that when we're doing tail to tail. So if I tell you, if I tell you 5 kilogram meters per second east, compare that to 5 kilogram meters per second west, and then compare that to 7 kilogram meters per second west. Okay. It's just arrows. The length here would be that. The length here would be this. Same length, different arrowhead, but this one would be longer. I hope that makes sense. That one will be longer. It's just as simple as that. Grade 10. That one would be longer. All right. So let's move on to our next concept. Is everybody okay there? Everybody okay? Don't lose me. If we get the basics right, then we'll be able to do complex questions. But if we lose the basics, then complex questions become very, very difficult to do. The complex questions just require these simple basics that we are looking at together. Now, we can talk about, our next concept would be the change in velocity, which would cause us to talk about a change in momentum. What do I mean by a change in velocity? The velocity of an object can change, hence we can then talk about a change in momentum. So let's quickly look at the concept of change in momentum. So we're going gradually. I don't want to do too many calculations today. I want to build the notes. Change in momentum. And when I say change, you are physics learners, you automatically know that we should talk about delta P. I'm trying to make sure that you are following. So, change in momentum. And once I say change, like I said, we've done physics from grade 10, grade 11, it automatically tells you something, that change in momentum is basically what? Final momentum minus initial momentum. I hope that makes sense. So our change in momentum is going to be final minus initial momentum. Final momentum minus initial momentum. Are we still together? So it's going to be 1.5 hours of content. So you've got to pick up a pace. 1.5 hours of content. I won't go to any question paper. I'm just going to create little quick examples for us. Then you take the note, you read the note, you digest it, you underline things that you don't understand. When we come back for our lesson 2, we apply the notes. That's my intention. Now, but we do know that momentum is the product of mass and velocity. So I can have this as mass times the final velocity minus mass, because the velocity is what is changing. The object mass at this time is not changing. Are we good with that? The mass of the object is not changing at this time. Oh, so we can say the change in momentum, therefore, can be written as m vf minus vi if I factorize. Therefore, change in momentum is m change in velocity. Interesting. We're getting somewhere. The change in momentum is mass times the change in velocity. Remember, the mass of the object remains the same in this case. Mass of object remains the same. Only velocity changes. Let's look at 1 or 2 examples on this. Oh, I used to have multiple choice on this. But like I said, I'm only going to do notes now. Questions we will do later. So change in momentum. And by the way, our unit will still be the same, right? Because mass is there, it is still kilogram. Change in velocity is still velocity, meters per second plus direction. Now, our next slide will be very, very important because I'm going to look at some examples and some vector diagrams as well. Are we ready? Let's see, need to make sure everybody is on board and ready to move. Okay. Is there anyone still busy? If you are still busy, give me a thumbs down so that I'll wait for you. So didn't you just come in now? If you just came in now, Okay, we good. Lovely. So, are we good? All right, thank you to say it. So, all right, everybody looks good. Okay, we're looking at this concept of change in momentum. Let's see something here quickly. Examples of change in momentum. Examples. Examples. Okay, let's say what's this? A cricket ball. Yeah. I don't like this game. I don't even understand it. A cricket ball is thrown at a cricket ball, of mass. Let's add a mass. 0.25 kilogram. I don't know whether that's heavy. Is thrown at a velocity of 2 meters per second towards a man with a bat. A man with a bat. You know cricket, right? So the man uses or hits the ball at a velocity of 5 meters per second backwards. 1. Calculate initial momentum of the ball. 2. Final momentum of the ball. 3. Change in momentum of the ball. Then represent the initial, final, and change in a vector diagram. Okay. Give you a moment to write. You have 2 minutes to write that. Then we will calculate together. And Noku, Tegofato, you didn't share your report with me. I want to see what you were cooking. Would you share? Thank you. Noku ghosted me when I said share a report. You know I will call you. I don't have a problem. One more minute to write. And you can try to go ahead with this calculation. You can just try. It's very simple. You've been doing physics. You have your data, you have your formula. You can just substitute. All right, there we go. Thanks, Noku. Oh, this child was cooking. Proud of you, Nana. Okay, guys, are we done with the notes? Are we done? Okay, so a cricket ball of mass 0,2, I like to always read and understand what the examiner is saying. The mass is 0,25, so let's put that down. M is 0,25, okay? It's thrown at a velocity of 2 meters per second towards a man with a bat. Okay, so I don't know where the man is, whether the man is on my left or on my right, but that seems to me like an initial velocity. Why am I saying initial? Because we read on further to say the man hit the ball at a velocity of 5 meters per second backwards. That's my second velocity. Okay, so I'm going to come here and say, let's take towards as positive. Now, this is me taking care of vector now. So my initial velocity is positive 2, while my final velocity is -5. Please let me know if we are on board with what I just did. It is a vector quantity, so we must take our directions and we use signs. Please let me know if you are okay with that. Please, very, very important. This is the vector notation. This is the vector property here. Magnitude and direction. Our direction is represented with positives and negatives. Okay, number 1. Initial velocity. Mass times initial momentum, mass times initial velocity, 0,25 times 2. And what will this give us? 0,5 kilogram meters per second towards. the man with the bat. Direction is important. Towards. I cannot use left or right here because that was not mentioned. Neither can I use east and west. Is that okay with you? First one done, and that would be 3 marks. The direction is always important. What about my final momentum? Mass times final velocity, -5. Very important. -1,25, right? Now let's interpret that. This is 1,25. But what is that negative meaning? Away from the man with the bat. So we must be very clear with the directions that we are using. It's towards the man with the bat, positive. When it goes back, it's going away from the man with the bat. And then we can do the third one. Change in momentum, which is always the final minus the initial. And our final is -1,25 minus 0,5. And that would be what? -1,75. And that would be 1,75 kilogram. Is it a negative answer? All right, we said towards will be positive. So away would be negative. Away from man with bat. Once we start looking at questions, we start using our left, right, east, and west. Let me know if everybody's okay with those 3. You're okay with the 1, 2, 3. Initial, final, and change. Especially the signs. Please, once you omit the signs, physics is now wrong. This is a vector quantity. Now the last one. Represent the initial, final, and change in a vector diagram. Okay, so I'm going to come here and use arrows. And I want you to look at what I'm going to do. I'm just going to pick a point to start from here. All right? So my initial, okay, I'm going to draw it towards my right, 0,5. Okay. Initial momentum. Now you would notice that the final momentum is way longer. Okay, so let's do this. I'm just going to shift it here. My final momentum is way longer, and it's in the opposite what? Direction. And please understand the maths here as well. Use calculations to guide yourself. Do you notice that 0,5, 1,25, and basically it's like we are adding the 2 numbers together. Do you see that? 1,25 and 0, it's almost as if we are adding them, but we are adding in the opposite direction. So I can come here now and do that. Final what? Momentum. in the opposite direction. Now, what is my change? My change is longer. It's the addition of both of them, but it's in away direction. Change in momentum. Let me just use this as boundary. Okay, that's not important anyway, but just make sure that it's the same to take care of the value. So if we write the value, the value would make a lot of sense. 0.25, 1.25, and this is 1.75. But negative, add, positive. And that's the point of connection. Sometimes we draw them, we don't combine. We can draw them out, not combining. Okay, sometimes we combine, doesn't really matter. You must just take note of the size. The size will guide you on the length. Did this make sense to us? I think I have one question that I'm going to allow you to do. I don't have my laptop here, but I could find it quickly. Let me find it. Once you are done with this page, I want you to try. Or let me do one more. There's a popular one that examiners like, and let me quickly dissolve it for you. Are we okay? Can we move? I have 3 examples that I want to do. 3 examples. Okay. Let me go for my second example. If you're still busy with the solution on the right, don't worry. I'm just going to clean my left-hand side. You can be busy with the right-hand side while I quickly create another question here. A car of mass 1,500 kilogram drives east. All right. At a speed of 80 meters per second. Now I've done 2 things there. I have said east, which is direction, and I used the word speed, which gives me the magnitude. But combination of that gives me velocity. All right. The driver suddenly decreases his speed to 20 meters per second as he approaches a red robot. Number 1, calculate A, initial momentum, B, final momentum, C, change in momentum, represent the initial, final, and change in a vector diagram. I believe everyone should be writing the question now. And after writing the question, I'm going to ask you to just try based on our first example. Try. So writing and you trying, you have 5 minutes. Writing the question and trying to see if you understand and you can do it, make an attempt. It's okay to get the first attempt wrong. Remember, don't just write the question. You are trying now using the example that we did before. You're trying. Okay, so what is our mass? 1500, right? Let's take east, since we have told. Let's take east as positive. Just gonna clean this. Take east as positive. So our initial velocity will be 80. Our final is 20. They are both positive. I hope you see that. The guy only slows down. The guy did not change direction. So the 20 meters per second, we're still moving east. Okay, so let's start throwing in all the formulas that we can have. Okay, I'm going to have to delete all of this. All right, what is the mass again? Mass is 1500 times 80. What will that be? That is 0, 4, 120 and 1, 2, 3. Is that what you got? Okay, kilogram meters per second, and it's positive, right? So east. If you don't write that east, your answer would be wrong. It is a vector quantity. The second one, 1500 multiplied by 20. All right, so that's 30, 1, 2, 3 kilogram meters per second. Also east, because it is positive. Number 3, what is our change in momentum? Final momentum minus initial, which is what? 30,000 minus 120,000, and that will be negative 90,000. Okay, and what is that telling us? 90,000 kilogram meters per second. If my east is positive, then my negative must be west. Did that make sense for us? Or to us rather? Just normal basic physics. You're not doing anything hectic, just normal physics. Normal so far. Now, if I have to represent all of this with vector diagrams, let's see. The initial is very long, 120,000. So, there, we can do that. It's the longest starting point, and it goes that way. What do you notice? The final is 30,000, right? Okay. Final is 30,000. Now, that should not be as long as the initial. Like I said, sometimes the examiners may combine them, and sometimes they may not combine. So I'm going to try to draw it not combining. Since it is, I wanted to see something, the beauty of it. I'm going to do that as my final. And the balance. So we could draw it anywhere, but just show, you see, the balance is my change in momentum. So this time around, I'm just trying to put them together like that. So you would notice that my first one, so this is just one of the ways of doing the diagrams, 120,000. This one is 30,000, while this one is what? Negative 90,000. So in a question, the examiner may draw it separately. You can also draw it separately, but be mindful of the length. You don't have to measure. Just use your eyes to gauge. Use your eyes to gauge. So some may draw it like that. You may see some, we could have the diagram also looking like this. It's also fine. You don't have to put it together. As long as the magnitude and the direction are taken care of. You see, we want to see that the negative is pointing in the opposite direction. The 90,000 is smaller than the 120, but bigger than the 30. The 30 is east, so it must be pointing to the east. The 120 is in the easterly direction, must be pointing there. And the negative 90 in the west. Those are the things we want to mark. We want to mark the magnitude and we want to mark the direction. Are we okay with this? Whether we draw it on one single line, whether we draw it on 3 lines, it really doesn't matter. What matters is the size and the direction. Okay. I have one more question for you. I know you are busy on the right hand side. This one I won't write so many things. I'm going to use a diagram. Example 3. I'm going to make this a multiple choice. Okay. I hope the diagram alone just tells you what the question is saying, right? That's physics for you. The object is moving towards maybe a wall or something. The mass of the object is m. It hits the wall and bounces back, but as it bounces back, it moves with the same velocity v. Which one of these 4 will be the correct change in momentum? Work it out for me and tell me your answer. Let's populate A, B, C, D. Yes, I want answers now, please. I want answers now. Whatever you think you got, one of them is correct. I'm looking for change in momentum. All right, I have 2 C's already. I have the third answer, also a C. Can populate, calculate. Oh, then there's a B. Okay. There's a B now. That's a C. So far there's no D, there's no A. We're moving between. Oh, there's A now. Okay. Changing to A. There's a B. Okay, so we have A, B, C. Nobody with a D yet? Yes, so it's the same ball. Look at the diagram. It's the same ball. The ball moves towards the wall, bounces away from the wall, and you can see the mass is m. All right, it's the same ball. It hits the wall with a velocity of v, and it bounces off the wall with the same velocity. Okay, let's mark. Thank you so much. I see a lot of answers. Beautiful, beautiful. I love when we participate. Makes it good. Okay, so what is our initial velocity? Let's pick towards. Now, this is one error you guys did not do. Towards as positive. That's one error. The initial velocity will be v, and the final velocity. Now, if you didn't do this, already your answer is wrong. Okay, what is my change in momentum? It is m vf minus vi. What is my final velocity? Negative v. What's my initial? V. What do you see? M into negative 2v. Negative 2 mv. The correct option is B. Please quickly take note of your errors. All right, I see a few B's. I saw Pomolo giving me B. Subsiso giving me B. Tejo giving me B. Noku giving me B. Yes, Musa, talk to me.
Sorry, sir. Can you please explain this in a more theoretical way? I don't know, but I don't understand.
Where are you lost? Which theory do you want me to use?
So, sir, firstly, I chose B, and then secondly, I chose A. Because in my head, sir, can I please explain what I thought?
Go ahead.
Before choosing
Go ahead.
A. Yeah. So, sir, look at the first ball at the top.
Yes.
You see? So these balls have the same masses and the same velocities. So the other ball at the top, was heading towards the wall.
Okay.
And then it bounced and then went backwards.
Yes.
So, sir, I was like, maybe the initial velocity is the same as the final velocity.
Yes.
So, firstly, I chose east as positive.
Great.
Okay. No. I see where I got confused. I see.
You see, I wanted you to find yourself, and I'm glad you did. So the problem was the direction.
Yeah.
So we're good. We're good now?
Yes, sir.
Okay, great. Guys, are we all okay? I purposely waited for you here because this is a common question in the exam. Very common. Very, very common. And the most answer that people choose is 0. And they get 0. Now, another way the examiner would ask, don't laugh, I'm serious. The examiner wants you to pick 0 because they know that if you pick 0, you get a 0. Now, another way they'll ask this is, what is the magnitude? Magnitude of the change in momentum. What would your answer be? I'm changing the question now. First, I said, what is the change in momentum? We got B. Now I'm changing the question. What is the magnitude of the change in momentum? What would your answer be? Same question, nothing is changing, but what is the magnitude of the change in momentum? You don't need to recalculate, guys. I'm just testing if you understand physics. You need to choose an option, Valerie. The magnitude. Beautiful. The magnitude means, yes, you have an answer which is negative 2 MV. The negative, you see, when we have negative 2 MV, the negative only tells us the direction. The 2 MV tells us the magnitude. So in this case, our answer would be A. So please always pay attention. Read the question. So if you didn't pay attention, you will get the questions wrong. Are we all good there? Everybody good? I'm glad we are understanding gradually. All right, beautiful. Now, let's quickly look at something. Newton's second law. And impulse. We will stop on Newton's second law and impulse for the day today. Then tomorrow we'll go on to look at collisions. We finish the whole topic tomorrow and then calculate the remaining days. Okay. So Newton's second law. I'm sure you guys remember Newton's second law, right? Okay. I'm sure you guys can state it. I'm not going to state it, but I'm going to write the formula. F net is equal to what? MA. We still remember that? F net equals to MA. Please be able to state that. Now, what is A? That's my question. What is acceleration? Acceleration is the rate of change of velocity. That is, A is delta V over delta T. We're going somewhere. Are we good? Okay. All right. Now, if I replace this there, therefore, do you notice that I can replace this and say F net instead of writing A? Oh, do you notice that? It therefore means that the net force is equal to, if we change this to words. Oh, by the way, hold on. Do you notice that we've seen this before? What is that? That is delta P. So it's equal to the rate of change of momentum. And this whole thing here is called Newton's second law. Not the one you know, but this one in terms of momentum. Newton's second law in terms of momentum. The net force is equal. So don't even cram it. Just know that F net is equal to that over that. And quickly, what does this mean? What does this mean? I want us to explore this. Now, as time increases, the net force will decrease. This is application now. Let's call it application. As time increases, the net force decreases if the change in momentum is constant. I want to explain what I just wrote here. As time increases, the net force decreases if the change in momentum is constant. And this is what we are going to write. We are going to say that F net is inversely proportional to time for the same change in momentum. That's very important. For the same change in momentum is very, very important. For the same change in momentum. We are going to see an application now. We are going to see an application and we will end today's session. What does this mean? This is physics now. This is a real day-to-day physics. We use this every single day. F net, we're saying as time increases, the net force decreases if the change in momentum is constant. I want to quickly explain constant change in momentum. Constant change in momentum. What does this mean? All right. Mass is the same, but velocity changes. Okay. From VI to VF. The time taken for this to happen for this change in velocity to occur has an impact on the force that acts on the object. The time taken for this change in velocity to occur has an impact. So I want to explain the application, so follow me. The time taken for this change in velocity to occur has a great impact on the force that acts on the object. And this is physics now. Okay, we want to go into what I just wrote, explain it, apply it, and we'll end our first lesson. Just waiting for you guys to write, so we go into that explanation in details quickly. Force and time are inversely proportional only if the change in momentum is constant. And I quickly want to explain that. Can we move on quickly? I just want to explain that change in momentum being constant, using a quick example. All right, we're good. Now, what do I mean by all of this story that I wrote there? I just want to explain that little part and then move into proper examples and application. If I have an object here and the initial velocity at this point is 100, and the object gets here and stops, okay, let's say the mass is 10 kg. But the time frame for the object to change its velocity, T1, the object could use 10 seconds and the object could use 20 seconds. This is what we mean. The object could have used 10 seconds and the object could have used 20 seconds. But do you notice that the only thing changing in the two scenarios is time? Because my change in momentum, which is change in mass or mass times velocity, is really not changing. My final velocity is 0 minus 100. Do you notice that this is not changing? But then the time for the two scenarios now changes. F net for 1. We said change in momentum over change in time 1. What is my change in momentum? But what is the time for the first one? 10. What's your answer? Negative 100. And it is force, Newton. What about F net 2? I want us to compare delta P over negative what? Over 20. Time is not negative. And what is this? That is what? 50. Do you notice the bigger the time, the lesser the force? The negative only gives us direction. Do you notice that? That the bigger the time, when the time is 20, the force was 50. But when the time is 10, the force is 100. Did you see that? That when time is 20 seconds, our F net is 50. But when the time is 10, so where do we have more force? We have more force when we have less time. Very important. We have more force when there is less time. And change in momentum is constant. How do we increase time? What's responsible? How do we increase time? Now, this is application now. And this is where I'm going to ask you to think away from your rooms. Okay, so we can think in the room as well, but think outside, think out of the box now. So, if we increase time when there is contact, this time is actually, how do we increase time of contact? Let me put that there. As the time of contact increases, what are the gadgets? Number one, the use of a seat belt in a car. The seat belt is not for metro cops. Ask the taxi drivers, they'll tell you it's for metro. When I use a seat belt, I am increasing my time of contact. So when somebody hits the brake, there's a longer time of contact to reduce the force of impact. Number 2, airbags. You know airbags, right? Airbags. It's like a pillow. So when an accident happens, it's soft. It's a pillow-like object. So, guys, it's like you jumping on your bed. Imagine your dining table at home. Guys, just imagine your dining table is your bed. Do you jump on the bed? Like, days when you're tired from school, boom, you just go and lie on the... No. If your bed is very hard, you don't. The bed is soft. And that softness will increase the time. That's why you don't feel pain. I'm sure we even do WWE, on our bed sometimes. You know what I mean? John Cena and all of those things. We practice around the Orton. The reason why we can use the bed is because it's soft. So we don't feel the pain. Yeah, you guys are laughing. The lesser the time, the more the force. Number 3, arrestor beds. This one is used for trucks on the highway. You can Google it for a good picture. I didn't know I would get here today. I normally have pictures. Arrestor beds. So when a truck is moving on the highway, you would see the sign. For those of you that have done your learners, okay, no, you guys will do your learners end of this year and next year. But Google arrestor beds. So when a truck loses its brake, they normally just go on that path. It is very rough so that it slows them down. All right. Crumble zones. Crumple zones in cars. Now, what is a crumple zone in a car? I'll explain that quickly. All right, crumple zones. This is applicable to cars. I wish I could just Google Google crumple zones for you. All right, let me see. I want to see if I can put these 3 pictures quickly. So your crumple zone, as I'm looking for a diagram, but I'll be explaining to you. All right. So the crumple zone in a car talks about what am I doing? Talks about the place, like you see the bonnet in front of the car, right? That's a crumple zone. Cars with bigger crumple zones are safer. All right? Cars with bigger crumple zones are safer. That's why a car with a bonnet is safer than a car without a bonnet. Let's show you, because some of you don't know cars. So let's try to get a picture. Crumple zone. I want you to see it. Or cars with a boot. Okay, you see, like your normal car, all right, will have a boot, right? Check your taxis. They don't have boots. Okay? Now, because they don't have boots, they are not as safe as... Oh, beautiful. Beautiful. I love this. This is what I'm looking for. So the 3 are actually here. Oh, no, I don't want all of you. I just only want the diagram. Where's my diagram? Okay, now we have music. Oh, there we go. Beautiful. Let me see if I can. So all of this are to ensure what? Safety. And all of this is just using one principle. They increase the time of contact. And if they increase the time of contact, why is it saving us that? If they increase the time of contact, then the force of impact will decrease. Okay, let me cheat the system. So all of this, you can see the crumple zone, that it takes time for this thing to crumble, all right? That time alone is working with this formula. F net inversely proportional to what? Time. With our formula F net and delta T. So as the time here increases, the force, this guy is going to feel a less force. Imagine if this car is like your Uno that doesn't have a front, or your, you know, those with no engine, your Kombi, you know. Kombi, you can even put your leg outside. If you can put a hole, your leg, you can be outside when the Kombi is driving. That one is not as safe. You know what I mean, right? So this is very important when you're buying a car. The longer, that's why go check most Mercedes-Benz, it's quite long in front. That's crumble zone. It takes time. As time increases, the force decreases. Your seat belt, your airbag, can you see the airbag? It's pillow. Your head goes into it. As your head goes into it, there's time of contact. Look at your seat belt. It increases the time. So anything that increases time will decrease force. I don't know if this makes sense. I can give you more examples. Let's look at more examples. Let me add one here. Speed humps. Have you ever been in a car where the driver did not see the speed humps? Have you ever been in a car? What happens? Your head is almost hitting the roof. Do you know why? Because the driver is running over, so there's less time. We all feel it. Boom! We shout. But when the driver sees the humps and slows down, what happens? We don't feel the force. I don't know if that is applicable. You can relate to what I'm saying, right? With that. All right. That's what we mean by F net and delta T. Let's check on arrestor beds so that you have a good picture of what arrestor beds are. All right, I'm sure on the highway, many of you are still going to travel. Probably your parents are still working. You would probably see that sign. So that's an arrestor bed, and you can see all the pictures. So Google some of this. You can, you have AI these days. You use AI for the wrong things. You guys are using ChatGPT to copy assignments and whatnot. Instead of asking, play me a video of an arrestor bed, a truck, how it works. No. You'll be using ChatGPT. Write me an essay of how to kill my teacher. Very funny things that you guys write. Okay. Yeah. So please, when we're done with the lesson, just use your phone, look for videos that can help you see how. I'm sure there'll be a video of a guy driving on the arrest. You can see this one. It's all sand. So this guy probably has lost his brake. So it's gravel. It's a gravel road, and that helps the car to stop by increasing the time. Are we okay there, everybody? Did that make sense? Did that make sense? Now, this same, let's do a few more applications. This same fundamental principle will be what is responsible for what I want to see. Let me see if I can get a good picture. A soccer ball, or let me see, hard versus a soft ball bouncing. So if I have two sport balls that are bouncing, okay, one hard and one soft, what's going to happen? Do you think they will reach the ground at the same time? They'll hit when they bounce. Do you think they will rise up at the same time and reach the same height? No, they will not. Okay, guys, please just Google Google some of these things. You can Google and see a video, okay? Google and see a video, but I'll just quickly give you a small note there. All right, so let's have a ground. We have a hard ball, and we have a soft one. Okay, when the hard one hits the ground, it will bounce up quickly and actually almost reach its original height. But when the soft one, and I'm going to quickly explain that, so these are applications, it might just reach here. The question is, why? Can we explain this? Why? The hard ball spends a shorter time on the ground than the soft ball. And since F net is inversely proportional to time for the same change in momentum, the ground exerts, or let me say, the hard ball, I'm going to bring in Newton's third law, exerts a bigger force on the ground than the soft ball. And Newton's third law, according to Newton's third, I hope you remember that. If object A exerts a force on object B will simultaneously exert the same force on object A, equal in magnitude, but opposite in direction. According to Newton's third law, the ground exerts a bigger force on the hard than the soft ball, making the hard ball reach a higher height than, let me say, a higher maximum height. Because I want to keep the velocities the same. I want to know if all my story here makes sense to you. Okay. Is there anyone who is lost? We are about to finish this. Is there anyone who is lost? There's something I want to bring in here before we go. So the softer ball will spend more time on the ground. I'll just look at two things quickly, and then you see no calculation today, no homework. Please read the note again before the class, because I'm going to then fly I'm going to ride over this and then pew, 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 fly. I promise you, I will be flying. The next class, I'll be on a broom. I'll be sitting on a broom. You know what that means? I'll be flying. All right, guys, are we good? Are we okay? You guys can laugh, hey? Can I move on? I want to just do 2 things with you here and end the session. Still on application. So you can see all the applications. So your seat belt, your speed humps, your arrestor beds. I think we mentioned 5 of them, crumple zones. All of them have one purpose: increase time to decrease the force. As the time of contact increases, the force of impact will decrease. So I just used the same explanation here. We have a hard ball and a soft ball. A hard ball, because it's hard, it hits the ground, boom, and goes up quickly. Shorter time, so it bounces higher. A soft ball will boom on the ground. That is longer time. You can imagine, okay, you're going to have holidays when your swimming balls, you know, those ones we use for swimming, all right, or the one you use for the gym, you know, those people that want to lose weight. Throw it down and boom, it stays on the ground. It doesn't even bounce that much. Why? Because of the longer time it takes on the ground, the force decreases. Hence, it has no force and energy to rise up again. Can I move to the next screen? I want to finish this now. I want us to consider still application. Consider 2 objects that collide. Then I'll look at the graph and we're done. Consider 2 objects in collision. Okay, let's try to see if we can get a truck Oh, this is a very high truck. My truck looks ugly. Very far from the ground. Okay, as compared to a car, this car, it will go into the tires of the Okay, idea is what counts. Don't worry about the car. Okay, idea is what counts. These guys are moving in opposite direction and they collide. We have a driver in the first one and a driver in the second one. Who do you think is likely to get more injured? The driver in A or the driver in B? Come talk to me. Who is likely to get more injured? Just use your common sense, then I'll use physics to explain. The driver in A or the driver in B? Okay, I see you guys. The driver in B, that means you watch accidents on the road. Okay. The driver in B is likely to get more injured. The question is why? After collision, the driver B is prone to more injury. And these are physics questions. You'll see that these are exam questions. And the question is why? Using principle of physics. Car B has a smaller mass than A. hence a smaller inertia. I hope you remember what inertia is. All right, the property of an object to resist change. So car B has a smaller mass than A, right? The time taken for car B to experience the same change in momentum as car A, and I'm sure you know that according to Newton's third law, the force of car B will be the same as experienced by the force of car A. That one we know according to Newton's third law. That's why I'm saying for the same change in momentum. All right? According to Newton's third law. The time taken for car B to experience the same change in momentum as car A is very small, and F net is inversely proportional to that for the same change in momentum. Hence, car B experiences more force of impact than car A. Is my explanation on point? Same story, guys. We're just using different applications. Same story. Same story. That's why you'll see the driver of car A even rushing to go help car B, and they were both in the accident. So every time you answer physics questions, please take note of how I'm answering. I compare, then I use a formula, then I conclude. Car B has a smaller mass than A, hence a smaller inertia. The time taken, that's where the mark is now. The time taken for car B to experience the same change in momentum, already that is force, because force is delta P over delta T. So I'm already mentioning time and delta P, that's force. And I'm bringing in Newton's third law. But the time is very small. And that's my formula. F net is inversely proportional to time. The shorter the time, the more the force. Hence, car B experiences more force of impact than car A. All right, let me see. The same forces apply to both cars, yes. Since driver B has a smaller mass, it will experience a greater acceleration in the direction of the force. Okay, if you want to bring in acceleration, that's still fine. But instead of that acceleration, we've just brought in the force. Driver A's car with its large mass will experience a smaller acceleration. The smaller car is likely to be more damaged due to greater acceleration. All right. Okay, if you are explaining in terms of acceleration, that's also good. But I wanted to explain in terms of change in momentum. Because once I bring that formula in, F net is inversely proportional to time. Can you see I'm saying for the same change in momentum? Because your acceleration is already in. So once, I don't want us to write too many words. Simply, good explanation, but Sophie rather. Sophie, but shorter words. Let's use simpler explanations. Okay, guys, this is what I want to do. And finally, quickly, for the day, I have one more slide that I would go through with you. One more slide. Can I move to the last slide? Okay. My last slide will be this. And this I really have to take you through Oh, no. Before I look at that, I forgot something. Okay. Now, remember, consider F net. We have this, right? If we cross multiply, what are we going to get? F net delta t. Okay, this is very important. We cannot end the day. I'll use the graph to end. F net delta t is called impulse, which is defined as the product of net force. Can you see? Product of net force and time taken for the force to act. On an object. That is called impulse. And our unit of impulse will be what? F net is, okay, let me do this. Impulse has no symbol, so we have to write it. Impulse is F net times delta t. This is Newton second. That's our unit. And on the other hand, what is this? Change in momentum. So you would notice this is the relationship between them. Impulse has the same magnitude as change in momentum. Impulse has the same magnitude. So an examiner would give you change in F net and time they want. So we can get so many things. From here we can get F net, we can get time, we can get mass, we can get velocity. So please take note of that. All right. Some people are going to tell you that impulse is the same as change in magnitude. Please refuse. They are not the same, but they are the same in magnitude. Let me quickly, while you are writing, please listen to me. They are not the same, but they are the same in magnitude by reason of the formula. Why are they not the same? What am I talking about, guys? If I have 100 Rand note and somebody has 250 Rand notes, are they the same? You need to be careful with your answer. Are they the same? 100 Rand note and 250 Rand notes. Are they the same? Can somebody answer me? Are they the same? I'm setting you up for failure here. Okay, you guys are giving me an outright answer of no. The answer is yes and no. They are the same in value because it's both 100 Rand, right? 100 Rand note and 250 Rand note. But they are not the same in color, in texture. Makes sense? That's the same thing that is happening here. Impulse has the same. That's why if you ask somebody if you have 100 Rand and you want to change it to 50 Rand, what do? Somebody gives you 250 Rand notes. Have they cheated you? No. But the 100 Rand is blue and the 50 Rand is red. But you have two of them. Makes sense, right? You know, when I was smaller, I used to fight with my younger sister when somebody gives us money. Okay, somebody's giving me a thumbs down. No, Musa? Unmute yourself.
Yes, sir.
Hello, Nana. How are you?
I'm doing okay, sir.
Okay. What would you prefer? Would you prefer 100 Rand note or 520 rands?
It's the same thing, sir.
Absolutely. So it's the same thing in magnitude, 100, 100. But if you look at the color of the notes, are they the same?
No, sir.
Good. That's what we're saying here. The magnitude of impulse is the same as the magnitude of change in momentum, but they are different quantities.
Oh, okay, sir.
You get the whole idea, right?
They have different units.
They have different meanings, they have different formulas, they have different definitions, but the sizes are the same. Make sense?
Yes, sir.
Yeah, you can have 520 rands and be laughing at somebody who has 100 rand, saying, I have more money than you. Say, hey, wait, now you only have one, I have five. I used to do that when I was young, when I was still small. Yeah, my sister and myself used to fight over that. Oh, I have more money, I have five. Then you have one, Shame. All right, so that is what's happening here. They have this, that's why I wrote here, impulse has the same magnitude as change in momentum, but they are not the same in concept. So people are going to tell you, no, impulse is the same thing as change in momentum. Quickly stop them. They say that is incomplete physics. It is not the same in concept, but it has the same magnitude because their meanings are completely different. Impulse is the product of the net force and the time taken for the object to act, for the force to act on an object, while change in momentum is the product of the mass and its change in velocity. All right, let me quickly end today's session. Guys, are we okay with this? I want to end the session now with something you should have learned in grade 10, but just to quickly make us see. All right, graphs, the graph concepts. Very, very important. This one will cut across all your physics. I'm going to just do two things today. Number one, multiply the y and x axis. If the formula exists, we did this in grade 10, then the quantity is the area of the shape. I'm going to explain this. It's the area of the shape. Like I said, I'll just do two of this concept. There are three of them. Multiply the y and x axis. If the formula exists, then the quantity is the area of the shape. Number two, divide the y by the x axis. If the formula exists, then the quantity is the gradient of the graph. I'll just put the number 3 note, but we'll look at it later. Rearrange formulas. I won't look at number 3 today. And align it to fit y equals to mx plus c. Then compare. Only applies to straight line graphs. Okay. I'm just going to look at number 1 and number 2. 5-10 minutes we should be done, depending on how fast we write. Multiply the y and the x. If the formula exists, then the quantity is the area of the shape. While you're writing, I'm going to be busy here, drawing different graphs. We're just going to look at different scenarios, be prepared for anything. Okay, are we ready? I don't know if you are done with those 3 points on graphs. I've got a whole lesson on graphs on YouTube. Probably one of these I'll look for it and share it with you. Almost an hour lesson just talking about graphs. All right, now, so if you look at number 1, the first graph that I have there rather, we have a y-axis and the x. Let's follow number 1. Multiply the y and the x. Okay, what's on the y? Let's see. We call it the product. Okay, let's multiply. Let's see if it multiply. Y times x. What would that be? F net. Okay. Question. Have you seen this formula today? Yes or no? Here you have to know your formulas now. Okay, this formula exists, right? So I'm going to put a tick on it. Oh, great. It exists. Yes. That's what I mean by if the formula exists. And what is this? What is this quantity? This quantity is called what? The impulse. Now, my next statement says, if the formula exists, then the quantity is the area of the shape. What shape is this? It's a rectangle. Oh, it simply means that the impulse here is simply the area of the rectangle, which is length times breadth. Does that make sense to you? We're doing this in grade 10 when we're looking up for gradient, velocity, distance covered. What if I divide? From the formulas we wrote today, do you think this formula exists? Check your notes. The formulas we wrote today were what? Momentum is mv. We have F net is ma. We have F net is delta P over delta T. F net is M delta V. You would notice that in all of this, F net over delta T does not exist. No, it doesn't. F net, there's no way you are going to write F net over delta T. You'll be doing magic. You will not be doing maths. You must just have a circus. You will be doing magic. F net, because if you cross multiply, you have F net times delta T. So this formula does not exist. We don't need to worry about the gradient. Does not exist. And that's all we're doing. I'll do one more example with you. Did it make sense though? So an examiner will ask you to calculate impulse. They are simply telling you to multiply, find the area of that box, that's all. Let's look at one more, or maybe two if I can. All right, let's see. While you're drawing that, I'll just draw my third one. And this third one was actually tested either 2 years ago. Yeah, I think it must, no, last year. It must be last year. It must be last year. All right. Look at the graph number 2, the one on the left-hand side. I'm sure you're done drawing. Which formula exists? Let's start by multiplying. If we multiply, it is the product delta P times delta T. And if we divide, which one is existing? Number 1 or number 2? Look at the formulas in your book. Which one exists? The first one or the second one? Kazeka says the divide one. All right, so and Tehofata says number 2. There's no magic of maths that you will do. Number 1 does not exist. Okay, so it doesn't exist. All right. Number 2 exists. Now, what is number 2? What quantity is that? Check your notes. It's right there. Delta P over delta T. We do have that thing is equal to something. What is that quantity equal to? So this is physics now. Guys, this is going to affect all your physics. This, in this metric here. All topics will be affected. Thank you, Latoya. Thank you, Kazeka. All right, so that exists. And because it exists, it means our net force will simply be equal to what? The gradient of a graph. So if the examiner asks you to calculate F for F net, what do you look for? Gradient. Gradient. Did it make sense? That's how we use graphs. This is how we use graphs. And the last one for today, if we multiply, which one is existing? Number 1 or number 2? I think this one is similar to the one we looked at earlier on. Number 1 exists, right? This one is not existing. And what is this equal to? This, we said, could be impulse. And in terms of size, change in momentum. So the examiner can ask you to find either change in momentum, and this time around it's going to be what? The area, because it's multiplication of the triangle. Half base times height. Half base. Thank you, Nomusa. Impulse. So the examiner can give you this graph and tell you to find change in momentum. You just quickly need to know, oh, but the magnitude of change in momentum is the same as the magnitude of impulse. So I do not need the mass and the velocity. I can use F net and time to calculate the change in momentum. I hope it makes sense. Once I get impulse, the answer I get is the same answer for change in momentum. Only the units will be different. And I'm going to play with units with you very soon. You're going to see that the units, we can actually maneuver units. We can maneuver and just play with units. But for today, I'm done. But if you want me, I can play with one unit for you. Just play with units. Just enjoy physics, you know. For 30 seconds, I can just play with one unit, impulse, and change in momentum. I think we can try. Let's just play with one, because you must know this manipulation for physics. All right, I'll wait for everyone to finish on this page. Give me a thumbs up. Wow, this is so detailed, guys. Very detailed. When you do this at school, you're just going to be cruising. You are going to be cruising, I'm telling you. You'll be raising your hand. Can I explain? Can I explain? Can I explain? All right, let's just play with one dynamics of formulas. Okay, look at this. If I start by saying impulse, which is what? F net times, what's my unit here? It's Newton and that, right? But do you remember that this same F net is MA, right? So it means the Newton is kilogram, that's my mass. What is my acceleration? Meters per second squared. I hope you remember this. I just wanted to see the fun. And the examiners will use multiple choice to test you on this one. So my F net is Newton, which is MA. M is kilogram. Acceleration is meters per second. Now, let's bring it back in here. Let's see what we are going to get. kg, meters per second squared, multiplied by seconds. Laws of exponents. What would that be? kg. Remember, if it's the same base, we do what? Add the exponents. 1 minus 2. Oh, what is this? Mass. What is this? Velocity. Look at where we are. We are back at change in momentum. The beauty of maths and physics together. So an examiner can play around with you. Check. This is how they ask you. This is how they'll ask you, so that you say, what are we doing? Is it necessary? Impulse can be measured as A, B, C, and D. Kilogram, meters per second squared. Kilogram, meters per second. Kilogram. Look at this. This is how they are going to throw this in an exam. Impulse can be measured as, or can be measured equivalently. Let me put the word equivalently. Equivalently as. Now, in your head, when now you are thinking, what is impulse? Okay, you bring out the definition. Impulse is what? F net times delta T. All right. Okay, F net is Newton, time is seconds. Oh, yes. Oh, then you check. This one has a negative 1 on top. Wrong. What do I need to do? What do I need to do? Now you start breaking things down. What is this? Oh, F net is MA, and that is my newtons. Okay, let me break it down. Kilogram. Acceleration is meters per second square. Kg, loss of exponents. 1 minus 2 minus 1. Ta-da! B. This is not guessing. Mini, mini, money, mo. Bless the bless. Please, we don't do all of that. This is not time to do that. Marty, no. You know, let us do funny things. Some of you close your eyes, you move your pen round, and then you go wherever you stop. That's where you choose, and you find out that you are stopping right here, where there's no option. That's where you stop, where there's no option. Okay, guys. So please, the reason for my slow teaching is for us to pick information, and that's what's going to help us with multiple choice. I write lots of notes. There's a lot of answers in the notes that I gave you. Here is my principle. After giving you a note, if the note cannot answer questions, that note is useless. That's my principle. The note must be able to deal with questions when I'm not there. That's why you have a note. So your note is a memo. All the answers for physics are in the note. You are supposed to extract. So please, before the next session, take a moment, read line by line. Check, where is it that I don't understand? I want to ask this guy. I'm going to ask him, because I'm going to give you room to ask me before we continue. That from the last lesson, is there anywhere in your notes where you felt you didn't understand? Let's quickly clear the air, because we are going to be building more and more. Our next lesson, guys, it's calculation. So please come be ready. Calculators on the ball. It's fire for fire. We'll be done with this topic, and then we just spend 2 more days asking questions and attempting questions. Graph, simultaneous word problems. My good learners, have a beautiful and a lovely, lovely evening. Remember, classes are going to begin shortly. The weekly classes will begin shortly. Please make sure you're part of it, and make sure you also follow. There's a lot of short lessons that I have on TikTok, YouTube, blah, 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 blah. Make sure you subscribe so that you'll get notified anytime we do post. But this is Momentum Lesson 1. 2 definitions today. We defined momentum, product of mass and velocity, and we defined impulse. Impulse is the product of net force and time. All right. Good night, everybody. Thank you for the claps. Thank you for the vuvuzeling. Thank you for the hululating. Goodbye. Awesome, awesome. Goodbye, goodbye, goodbye. Good claps. The claps is so loud. Thank you. Catch you tomorrow, guys. Bye-bye.